One of the most bizarre and counterintuitive principles in all of physics, a quantum mechanical rule so strange that it defies every intuition we have about how the world should work. The chair you're sitting in, the floor beneath your feet, even your own body maintains its solid structure not because of forces pushing things together, but because of a quantum principle that absolutely forbids certain particles from occupying the same space. The Pauli Exclusion Principle, discovered in 1925 by Wolfgang Pauli, states that no two fermions particles like electrons, protons, and neutrons can exist in exactly the same quantum state simultaneously. This might sound like an abstract rule from the depths of theoretical physics, and it's actually the reason why matter has volume, why you don't fall through the ground, and why the entire solid world around you doesn't collapse into a point of infinite density. Here's what makes this absolutely mind-bending. The force that keeps matter solid isn't really a force at all in the conventional sense. It has a quantum mechanical constraint that creates what physicists call degeneracy pressure, an effective repulsion that emerges purely from the mathematics of quantum mechanics, and the fundamental requirement that identical fermions must occupy different quantum states. Without the Pauli exclusion principle, every atom in your body would collapse as electrons spiraled into atomic nuclei. Every solid object would compress to near zero volume as all particles tried to occupy the same lowest energy state. The entire material world as we experience it, from the keyboard you're typing onto the mountains and oceans of Earth itself, exists only because quantum mechanics absolutely forbids this collapse. The numbers involved are staggering. The exclusion principle operating in the atoms of a typical solid creates pressures that exceed atmospheric pressure by factors of billions. We're talking about quantum mechanical forces so powerful that they can support the weight of entire planets against gravitational collapse. White dwarf stars, objects with masses comparable to our Sun compressed into Earth-sized volumes, are held up entirely by electron degeneracy pressure rising from the Pauli exclusion principle. But here's where it gets truly extraordinary. This quantum mechanical principle doesn't just prevent matter from collapsing, it actively determines the mechanical properties we experience every day. The hardness of diamond, the flexibility of rubber, the conductivity of metals, even the transparency of glass all emerge from how electrons arrange themselves in quantum states that obey Pauli exclusion. On requirements, you need to understand something profound about what we're exploring tonight. This isn't just another physics curiosity about quantum mechanics. The Pauli exclusion principle represents the fundamental bridge between the microscopic quantum world and the macroscopic classical world we inhabit. It's the reason why quantum mechanics, despite being completely invisible at human scales, determines every material property we experience in daily life. Recent advances in quantum materials science have revealed applications of exclusion principle physics that seem like science fiction. Researchers at MIT have developed materials that can switch between solid and liquid states by manipulating electron quantum state occupancy. Scientists at Stanford have created quantum metamaterials that exhibit mechanical properties impossible for any classical material by exploiting exclusion principle constraints on electron arrangements. The technological implications extend far beyond just understanding existing materials. Quantum computing relies fundamentally on controlling electron spin states that obey Pauli exclusion rules. Superconductor technology depends on electron pairing that temporarily circumvents normal exclusion constraints. Even biological processes like photosynthesis and enzymatic reactions operate through electron arrangements governed by exclusion principle requirements. But perhaps most remarkably, the Pauli exclusion principle reveals something deep about the nature of identity and distinguishability in quantum mechanics. The principle applies only to identical particles that are truly indistinguishable in every physical property. This creates a universe where particle identity isn't just a labeling convention but a fundamental physical property that determines how matter can organize itself into complex structures. Recent discoveries in topological quantum materials have revealed that exclusion principle physics can create exotic states of matter with properties that have no classical analogs. These materials can exhibit fractional quantum Hall effects where electrons behave as if they carry fractions of the fundamental electron charge, purely through exclusion principle constraints on their quantum state arrangements. Tonight, we're going to journey from the fundamental quantum mechanical origins of the exclusion principle, through its role in atomic structure and chemical bonding, to its manifestations in solid-state physics and its technological applications in quantum devices. You'll discover why this seemingly abstract quantum rule represents one of the most powerful organizing principles in the universe, a principle that makes possible everything from the stability of atoms to the existence of complex materials to the operation of quantum computers. If you are fascinated by how quantum mechanics shapes the everyday world and determines the fundamental properties of matter itself, hit that subscribe button and give this video a thumbs up. And here is a question that will make perfect sense by the end. If you could temporarily turn off the Pauli exclusion principle in a small region of space, what would happen to ordinary matter in that region? Drop your most creative predictions in the comments. I'll pin the most insightful quantum mechanical analysis. We're about to discover that one of the strangest rules in quantum mechanics is actually responsive. Love for one of the most fundamental features of our everyday experience, the fact that solid matter has volume, structure, and mechanical properties. The exclusion principle that operates on subatomic scales determines whether you sink through the floor or stand firmly on solid ground. The journey starts with understanding what fermions are and why their quantum nature requires exclusion. But it ends with recognizing that this principle represents one of the fundamental organizing forces that makes complex matter possible throughout the universe. Fermion fundamentals. The story of why matter is solid begins with understanding fermions, a class of particles that includes electrons, protons, neutrons, and many other fundamental particles that obey quantum mechanical statistics so strange they literally cannot coexist in identical quantum states, creating the foundation for all material properties we observe in the macroscopic world. To understand fermions, we need to grasp that quantum mechanics divides all particles in the universe into exactly two categories based on their intrinsic angular momentum or spin. Particles with half-integer spin values 1/2, 3/2, 5/2, etc. are called fermions, named after Enrico Fermi, who first described their statistical behavior. Particles with integer spin values 0, 1, 2, etc. are called bosons, named after Satyendra Bose. This classification isn't just a convenient organizational scheme, it represents a fundamental division in how particles can behave collectively. Dr. Wolfgang Pauli discovered in 1925 that fermions obey an absolute prohibition. No two fermions can exist in exactly the same quantum state simultaneously. This Pauli exclusion principle has no analog in classical physics and emerges purely from the mathematical structure of quantum mechanics. The quantum mechanical foundation of fermion behavior lies in the wave nature of matter described by quantum field theory. Fermions are described by wave functions that are antisymmetric under particle exchange. If you swap the quantum labels of two identical fermions, the wave function changes sign. This mathematical requirement leads directly to exclusion principle constraints. Dr. Maury Gell-Mann's analysis of particle physics reveals that the electron, which determines most chemical and material properties, carries spin 1/2 and therefore obeys fermionic statistics. Each electron requires a complete quantum state specification including position, momentum, and spin orientation. The exclusion principle means that no two electrons can share identical specifications for all these quantum numbers simultaneously. Recent experiments at CERN and other particle physics facilities have confirmed that all fundamental matter particles, quarks, electrons, muons, neutrinos exhibit fermionic behavior. Dr. Frank Wilczek's theoretical work shows that this is accidental. The stability of matter itself requires that the building blocks of atoms behave as fermions rather than bosons. But fermion behavior creates effects that seem to violate common sense about how particles should interact. And like classical particles that can pile up in the same location without restriction, fermions actively avoid each other quantum mechanically. This avoidance isn't due to electrical repulsion or any classical force, it is a purely quantum mechanical effect that emerges from exclusion requirements. The mathematical description of fermion systems involves Fermi-Dirac statistics. Developed independently by Fermi and Paul Dirac in the 1920s. These statistics describe how fermions distribute themselves among available quantum states, always respecting the constraint that each state can contain at most one fermion. Dr. Dirac's equation reveals that this statistical behavior emerges inevitably from the relativistic quantum mechanics of spin 1/2 particles. Consider what this means for the electrons in atoms. Each electron orbital described by quantum numbers n, l, m, and spin can contain at most 2 electrons, and only if they have opposite spins. This constraint determines the entire structure of the periodic table, chemical bonding, and ultimately all material properties we observe in nature. Recent quantum simulation experiments by Dr. Emil Bloch at the Max Planck Institute have enabled direct observation of fermion exclusion effects using ultra-cold atoms trapped in optical lattices. These experiments show fermions spreading out to avoid each other even when attractive interactions would classically favor clustering, demonstrating pure exclusion principle physics in controlled laboratory conditions. The exclusion principle also explains why fermions resist compression in ways that have no classical analog. When you try to squeeze fermions into smaller volumes, they're forced into higher energy quantum states because lower energy states are already occupied. This creates degeneracy pressure that opposes compression even in the absence of any attractive or repulsive forces between particles. Dr. Subramanian Chandrasekhar's Nobel Prize-winning work demonstrated that degeneracy pressure from electrons can support entire stellar masses against gravitational collapse. White dwarf stars represent the ultimate expression of electron degeneracy pressure objects where quantum mechanical exclusion effects operating on atomic scales determine the fate of stellar mass objects. But fermion fundamentals extend beyond just electrons to include the nuclear particles that provide atomic mass. Protons and neutrons are composite fermions made from quarks, and they also obey Pauli exclusion within atomic nuclei. This nuclear exclusion determines nuclear binding energies, radioactive decay processes, and the stability of different isotopes. Recent advances in nuclear physics have revealed that exclusion effects between nucleons create nuclear shells analogous to electron shells in atoms. Dr. Maria Goeppert-Meyer's theoretical work showed that nuclear stability depends on nucleons filling discrete energy levels according to exclusion principle requirements, explaining why certain magic numbers of protons and neutrons create particularly stable nuclei. The quantum field theory description of fermions reveals even more fundamental connections. Dr. Steven Weinberg's analysis shows that fermions and bosons represent only two possible types of quantum fields consistent with special relativity and quantum mechanics. This isn't just an observed fact about nature, it's a mathematical requirement of fundamental physics. Experimental verification of fermion exclusion has been demonstrated with extraordinary precision. Dr. Elliott Lieb's mathematical proofs show that violation of Pauli exclusion for electrons would lead to observable changes in atomic spectra that disagree with measurements by many orders of magnitude. The exclusion principle has been tested more precisely than almost any other principle in physics. But perhaps the most remarkable aspect of fermion behavior involves its connection to the stability of matter itself. Drive, Freeman Dyson and Dr. Andrew Leonard proved mathematically that matter would be unstable without exclusion principle constraints on electron behavior. Without Pauli exclusion, atoms would collapse and all matter would become infinitely dense. Understanding fermion fundamentals also illuminates why exclusion effects become more important as particle density increases. In dilute systems, particles rarely encounter exclusion constraints because plenty of quantum states remain available. In dense systems, exclusion constraints dominate physics as particles are forced into high-energy states by an availability of low-energy states. Recent condensed matter experiments have revealed fermion liquids where exclusion principle physics creates collective behaviors impossible for classical fluids. Dr. David Pines' analysis shows that liquid helium-3, composed of fermionic helium atoms, exhibits properties directly traceable to exclusion constraints on atomic quantum states. The technological applications of fermion physics extend throughout modern electronics and quantum devices. Every semiconductor device relies on exclusion principle constraints that determine how electrons can occupy energy bands in crystalline materials. Dr. John Bardine's transistor invention fundamentally depends on controlling electron occupancy of quantum states that obey fermionic statistics. Modern quantum computing implementations often use fermionic systems like trapped ions or quantum dots where individual fermions serve as qubits. Dr. David DiVincenzo's analysis shows that fermionic qubits offer certain advantages over bosonic systems because exclusion constraints provide natural protection against certain types of quantum errors, but fermion fundamentals also reveal deep connections between quantum mechanics and thermodynamics. The statistical behavior of fermions determines heat capacities, electrical conductivities, and thermal properties of materials through the relationship between exclusion constraints and how energy distributes among quantum states. Understanding why fermions obey exclusion while bosons don't requires appreciating the deep mathematical structure of quantum field theory. Dr. Sidney Coleman's analysis reveals that exclusion versus non-exclusion behavior emerges from topological properties of quantum wave functions that have no classical analogs. Recent theoretical work suggests that fermion behavior might connect to fundamental questions about space and time structure. Some approaches to quantum gravity propose that spacetime itself might emerge from entanglement properties of fermionic quantum fields, making exclusion principle physics relevant to the deepest questions about reality's fundamental structure. As we prepare to explore the historical discovery of the exclusion principle and its revolutionary impact on atomic theory, remember that fermion fundamentals represent one of the most important organizing principles in the universe, a principle that determines everything from atomic structure to stellar evolution through pure quantum mechanical constraints on particle behavior. The question that emerges from understanding fermion fundamentals is profound. If the stability and structure of all matter depends on this quantum mechanical prohibition against identical particle states, what does this reveal about the fundamental nature of identity and distinguishability in quantum reality? Pauli's discovery, the discovery of the exclusion principle, represents one of the most crucial moments in the history of physics, a breakthrough that emerged from Wolfgang Pauli's brilliant analysis of atomic spectra in 1925, revolutionizing our understanding of atomic structure and establishing quantum mechanics as the foundation for comprehending why matter behaves the way it does at the most fundamental level. In the early 1920s, atomic physics faced a crisis that threatened the entire foundation of quantum theory. The Bohr model of atomic structure, which had successfully explained hydrogen atomic spectra, completely failed when applied to more complex atoms. Dr. Niels Bohr's circular and elliptical orbital models predicted far more spectral lines than were actually observed, creating what physicists call the spectroscopic puzzle. Wolfgang Pauli, working at the University of Hamburg under Max Born, approached this problem with characteristic mathematical rigor and physical insight. Born described Pauli as having an almost supernatural ability to identify the essential physics hidden within complex experimental data. Pauli's notebooks from this period reveal his systematic analysis of how electron arrangements in atoms might be constrained by previously unknown quantum mechanical principles. The breakthrough came when Pauli realized that the spectroscopic data could be explained if electrons were somehow forbidden from occupying identical quantum states within atoms. This wasn't just a convenient assumption. Pauli recognized that such a principle would have profound consequences for all atomic physics and chemistry. Dr. Ralph Kronig had suggested in 1924 that electrons might possess an intrinsic angular momentum, later called spin, but Pauli initially rejected this idea as too classical. However, the exclusion principle required exactly such an additional quantum number to make mathematical sense. Electrons needed for quantum numbers free for orbital motion plus spin to fully specify their quantum states. Pauli's formulation was beautifully simple yet revolutionary. Es kann niemals zwei oder mehr äquivalente Elektronen im Atom geben. For die Starkenfeldern die wird aller Quantenzahlen bestimmen, there can never be two or more equivalent electrons in an atom for which the values of all quantum numbers are the same in strong fields. Recent historical analysis by Dr. Abraham Page reveals that Pauli initially hesitated to publish his principle because its implications seemed so radical. The idea that quantum mechanics could impose absolute prohibitions on particle arrangements had no precedent in classical physics. Pauli worried that such action at a distance constraints might violate relativity or causality principles, but experimental evidence overwhelmingly supported Pauli's principle. The electron configurations that explained atomic spectra, chemical periodicity, and materials properties all required exclusion principle constraints. Dr. Edmund Stoner had independently arrived at similar conclusions through analysis of X-ray spectroscopy data, providing crucial experimental support for Pauli's theoretical insight. The mathematical formulation of the exclusion principle required developing new statistical mechanics for quantum systems. Fermi and Dirac independently developed the statistical framework that described systems of identical fermions obeying exclusion constraints. This Fermi-Dirac statistics represented a completely new branch of statistical physics with no classical analog. Dr. Paul Dirac's relativistic quantum mechanics, developed in 1928, provided the theoretical foundation explaining why exclusion behavior emerged from fundamental quantum field theory. Dirac's equation revealed that particles with half-integer spin automatically obey antisymmetric statistics that lead to exclusion principle constraints. Pauli's discovery also resolved the long-standing puzzle of chemical periodicity. Dmitry Mendeleev's periodic table organization could finally be understood as reflecting electron shell structure determined by exclusion principle requirements. Dr. Linus Pauling's subsequent work on chemical bonding showed how exclusion constraints determine molecular structure and chemical reactivity. The immediate impact on atomic physics was revolutionary. Dr. Arnold Sommerfeld's extended Bohr model could now explain complex atomic spectra by incorporating exclusion principle constraints on electron arrangements. The Aufbau principle, building up electron configurations by filling lowest energy states while respecting exclusion, provided systematic understanding of all atomic structure. But Pauli's discovery raised profound questions about the nature of quantum mechanical reality. The exclusion principle seemed to require instantaneous action at a distance of electrons throughout n atoms somehow knowing about each other as quantum states to avoid forbidden configurations. This challenged basic assumptions about locality and causality in physical interactions. Recent analysis of Pauli's correspondence reveals his deep philosophical concerns about these implications. Letters to Heisenberg and Bohr show Pauli struggling with how quantum mechanics could impose global constraints on particle behavior without violating relativity. These concerns eventually led to quantum field theory developments that reconciled exclusion with relativistic causality. The experimental verification of Pauli's principle came from multiple sources. X-ray spectroscopy revealed electron shell structure consistent with exclusion requirements. Chemical bonding studies confirmed that electron pairing in molecules followed exclusion constraints. Magnetic properties of materials exhibited behaviors explainable only through fermionic electron statistics. Derived out Otto Stern and Dr. Walther Gerlach's famous experiment demonstrating electron spin provided crucial experimental foundation for Pauli's principle. Their observation of discrete spin states confirmed that electrons possessed the additional quantum number required for exclusion principle formulations to work correctly. Pauli's Nobel Prize in Physics in 1945 recognized the exclusion principle as a new law of nature. The Nobel Committee emphasized that this principle provided foundation for understanding atomic structure, chemical bonding, and the mechanical properties of matter. Pauli's discovery had unified atomic physics, chemistry, and materials science under single quantum mechanical framework, but the exclusion principle also opened new frontiers in theoretical physics. Dr. Enrico Fermi's application of exclusion statistics to nuclear physics explained nuclear shell structure and stability. Dr. Subramanian Chandrasekhar's astrophysical applications showed how exclusion principle physics determines stellar evolution and white dwarf stability. The philosophical implications of Pauli's discovery extended beyond just physics to questions about reductionism and emergence in complex systems. The exclusion principle demonstrated how quantum mechanical constraints on microscopic particles could determine macroscopic properties of materials, bridging quantum and classical physics in unprecedented ways. Recent historical scholarship by Dr. Nancy Cartwright reveals that Pauli's exclusion principle influenced broader development of quantum field theory and particle physics. The constraint-based approach to quantum mechanics pioneered by Pauli became central to gauge theories and standard model physics. Pauli's personality and working style contributed to his discovery's impact. Colleagues described him as the conscience of physics, someone who could identify conceptual problems and inconsistencies that others missed. His famous Pauli effect, where experimental equipment would malfunction in his presence, became legendary among physicists. The technical details of Pauli's derivation involved sophisticated group theory and representation theory mathematics. Dr. Hermann Weyl's analysis showed how exclusion principle requirements emerged naturally from symmetry properties of quantum mechanical wave functions under particle exchange operations. Modern understanding reveals that Pauli's exclusion principle represents just one aspect of broader quantum statistical behavior. Fermions obey exclusion while bosons exhibit opposite inclusive behavior where multiple particles prefer identical quantum states. This fermion-boson dichotomy determines all quantum many-body physics. Recent quantum simulation experiments have enabled direct observation of exclusion principle physics in controlled laboratory conditions. Dr. Immanuel Bloch's optical lattice experiments with ultra-cold atoms provide quantum gas microscopes that can visualize individual fermions avoiding each other according to Pauli constraints. But perhaps the most remarkable aspect of Pauli's discovery involves its continuing relevance to cutting-edge physics research, quantum computing, topological materials, and exotic quantum phases all depend fundamentally on exclusion principle physics. Pauli's 1925 insight continues driving modern technological developments in quantum materials and devices. Understanding Pauli's discovery also illuminates how revolutionary scientific breakthroughs often emerge from careful analysis of experimental anomalies. The spectroscopic puzzle that motivated Pauli's work seemed like a technical detail, but solving it required recognizing completely new organizing principles in quantum mechanics. The exclusion principle's discovery demonstrates the power of theoretical physics to uncover hidden order in complex experimental data. Pauli's mathematical insight revealed that apparent complexity in atomic spectra actually reflected simple quantum mechanical constraints operating on electronic structure. As we prepare to explore how the exclusion principle determines atomic structure through electron shell organization, remember that Pauli's discovery represents one of the most important conceptual breakthroughs in modern physics, a principle that continues to determine our understanding of matter's fundamental properties. The question that emerges from understanding Pauli's discovery is profound. If this principle emerged from analyzing atomic spectra but applies to all fermions throughout the universe, what does this reveal about the deep mathematical connections between local experimental observations and universal physical laws? Electron shells. The organization of electrons into shells or on atomic nuclei represents one of the most beautiful manifestations of the Pauli exclusion principle, a quantum mechanical architecture that determines not only atomic structure but also chemical behavior, materials properties, and ultimately why different elements exhibit the distinctive characteristics that make complex chemistry and materials science possible. To understand electron shell structure, we need to appreciate that electrons in atoms occupy specific quantum states characterized by 4 quantum numbers, the principal quantum number and determining energy level, the orbital angular momentum quantum number all determining orbital shape, the magnetic quantum number m_all determining orbital orientation, and the spin quantum number m_s either 1/2 or -1/2. The Pauli exclusion principle requires that no 2 electrons in an atom can have identical values for all 4 quantum numbers simultaneously. This constraint forces electrons to arrange themselves in a hierarchical structure of shells and subshells that can accommodate only specific maximum numbers of electrons before additional electrons must occupy higher energy states. Dr. Niels Bohr's correspondence principle, combined with Pauli exclusion, predicts that the innermost shell n = 1 can accommodate only 2 electrons with opposite spins in the same 1/2 orbital. The second shell n equals to can accommodate 8 electrons distributed among to south and to p orbitals. The third shell n equals 3 can accommodate 18 electrons among 3 south, 3p, and 3d orbitals. Recent X-ray photoelectron spectroscopy experiments have provided direct experimental verification of electron L structure. Dr. Kai Siegman's Nobel Prize-winning techniques enable measurement of electron binding energies with sufficient precision to map the detailed energy level structure that results from exclusion principle constraints on electron arrangements. The mathematical description of electron shells involves solving the Schrödinger equation for multi-electron atoms while incorporating exclusion principle constraints. Dr. Douglas Hartree and Dr. Vladimir Fock developed self-consistent field methods that approximate multi-electron wave functions as products of single electron orbitals, each occupied by at most 2 electrons with opposite spins, electron shells. But electron shell structure reveals subtle effects beyond simple orbital filling. The exclusion principle creates electron-electron repulsion effects that aren't due to electromagnetic interactions but rather emerge from quantum mechanical constraints on wave function overlap. Electrons with parallel spins are kept apart more effectively than electrons with antiparallel spins, leading to exchange energy effects. Dr. John Slater's analysis of atomic structure showed that these exchange effects significantly modify electron binding energies and atomic properties. The Slater rules for estimating atomic properties incorporate both direct electromagnetic interactions and indirect exclusion-related effects that determine experimental atomic spectra and chemical behavior. Recent computational quantum chemistry advances have enabled exact solution of Schrödinger equations for multi-electron atoms using Monte Carlo methods. Dr. Anderson's quantum Monte Carlo calculations reveal that exclusion principle effects account for approximately 10 to 30% of total electron binding energies in typical atoms. Demonstrating the crucial role of quantum statistics in atomic structure, the periodic table organization directly reflects electron shell structure determined by exclusion principle requirements. Elements with similar chemical properties occur at regular intervals corresponding to electron shell completion. Dr. Linus Pauling's analysis showed that chemical periodicity results entirely from exclusion principle constraints on electron arrangements in atomic ground states. Consider how exclusion principle physics determines the properties of specific elements. Hydrogen, with 1 electron, exhibits simple behavior because exclusion constraints don't apply. Helium, with 2 electrons filling the 1 south shell completely, exhibits chemical inertness because additional electrons must occupy much higher energy states. Lithium, with 3 electrons, has 1 electron in a higher energy to south state, making it chemically reactive. The exclusion principle also explains why certain electron configurations are particularly stable. Filled and half-filled subshells exhibit enhanced stability because exclusion principle constraints are satisfied in symmetric ways that minimize total electronic energy. This explains why chromium and manganese exhibit anomalous electron configurations that provide extra stability through exchange energy effects. Recent advances in atomic spectroscopy using synchrotron radiation sources have enabled detailed studies of electron shell structure in excited atomic states. Dr. Bernd-Sonntag's experiments reveal how exclusion principle constraints determine not only ground state electron arrangements but also the energies and lifetimes of excited electronic configurations. But electron shell physics extends beyond just isolated atoms to include interactions between atoms that determine chemical bonding and materials properties. When atoms approach each other, their electron shells overlap, creating molecular orbitals that must also satisfy exclusion principle requirements for the combined electronic system. Dr. Robert Mulliken's molecular orbital theory demonstrates how exclusion principle constraints determine molecular electronic structure. Bonding orbitals can accommodate 2 electrons with opposite spins, while antibonding orbitals also follow exclusion requirements. The balance between occupied bonding and antibonding states determines molecular stability and chemical reactivity. The technological applications of electron shell physics appear throughout materials science and electronic device engineering. Semiconductor behavior depends fundamentally on electron shell structure in crystalline solids, where exclusion principle constraints determine band structure and electronic transport properties. Dr. Felix Bloch's analysis of electrons in crystalline solids showed how exclusion principle requirements lead to energy band formation. Electrons in solids occupy Bloch states that extend throughout the crystal but must still satisfy exclusion constraints. This creates filled valence bands and empty conduction bands separated by energy gaps that determine electrical and optical properties. Recent experiments using scanning tunneling microscopy have enabled direct visualization of electron shell structure in individual atoms and molecules. Dr. Don Eigler's atomic manipulation experiments show how exclusion principle constraints determine the spatial distribution of electronic charge on atomic nuclei, providing direct confirmation of quantum mechanical predictions. But electron shell structure also reveals connections between atomic physics and nuclear physics through inner shell effects. High-energy processes can create vacancies in inner electron shells, leading to characteristic X-ray emission when outer electrons fill these vacancies. These transitions must satisfy exclusion principle requirements and selection rules that determine transition probabilities and energies. Understanding electron shells also illuminates how quantum mechanics bridges microscopic and macroscopic physics. The exclusion principle operating on individual electrons determines bulk properties of materials including mechanical strength, electrical conductivity, optical absorption, and thermal properties through collective electronic behavior in solids. Recent discoveries in quantum materials science have revealed exotic electron shell effects in artificial atomic structures. Quantum dots nanoscale semiconductor structures that confine electrons in 3 dimensions exhibit artificial atomic behavior where electron shell structure can be controlled through device geometry and external fields. Dr. Leo Cowenhoven's experiments with quantum dots demonstrate that exclusion principle physics applies not only to natural atoms, but to any system where fermions are confined in potential wells. These artificial atoms exhibit shell structure, magic number effects, and chemical periodicity analogous to natural atomic behavior. The mathematical framework describing electron shells involves sophisticated quantum many-body theory that accounts for exclusion principle constraints on multi-electron wave functions. Dr. Walter Kahn's density functional theory provides computational methods for calculating electron shell structure in complex atomic and molecular systems. But perhaps the most remarkable aspect of electron shell structure involves its role in enabling complex chemistry and biochemistry. The diversity of chemical bonding arrangements, molecular structures, and biochemical processes all depend on exclusion principle constraints that create the rich variety of electron configurations possible in multi-electron atomic systems. Modern quantum chemistry calculations reveal that exclusion principle effects determine not only ground state molecular structures but also chemical reaction pathways, transition state energies, and catalytic mechanisms. Dr. Roald Hoffmann's analysis of chemical reactivity shows how orbital symmetry and exclusion constraints determine which chemical reactions are allowed or forbidden. Understanding electron shells also provides insights into exotic atomic systems including highly charged ions, Rydberg atoms, and atoms in intense electromagnetic fields. These extreme conditions test exclusion principle physics under conditions far from normal atomic environments, revealing universal applicability of Pauli constraints. Recent experiments with ultra-cold atoms have enabled creation of artificial atoms using optical traps that confine neutral atoms in potential wells with tunable shell structure. These experiments provide controlled laboratory studies of exclusion principle physics under conditions where quantum statistics effects can be directly observed and manipulated. As we prepare to explore how electron shell structure determines chemical bonding through exclusion principle constraints on molecular orbital formation, remember that the shell architecture we've examined represents the quantum mechanical foundation for all chemical and materials properties in the natural world. The question that emerges from understanding electron shell structure is profound: if the entire periodic table organization and chemical behavior emerge from exclusion principle constraints on electron arrangements, what does this reveal about the deep connection between quantum mechanical principles and the complexity of chemical and biological systems? Chemical bonding, the formation of chemical bonds, the forces that hold atoms together in molecules and materials, represents one of the most direct manifestations of how the Pauli Exclusion Principle shapes macroscopic reality, creating the molecular architectures that enable everything from water and DNA to steel and semiconductors through quantum mechanical constraints on how electrons can be shared between atomic nuclei. Chemical bonding emerges when atoms approach closely enough that their electron shells overlap, creating molecular orbitals that must accommodate electrons from multiple atoms while strictly obeying exclusion principle requirements. This process doesn't involve any new forces beyond electromagnetism and quantum mechanics. Yet it creates the rich diversity of molecular structures that define chemistry and materials science. Dr. Linus Pauling's revolutionary work in the 1930s showed that chemical bonds form when atomic orbitals combine to create molecular orbitals that can house electrons in configurations that lower the total energy of the system. However, each molecular orbital can accommodate at most 2 electrons with opposite spins, exactly as required by the Pauli Exclusion Principle. The simplest example involves hydrogen molecule formation. When 2 hydrogen atoms approach each other, their 1s atomic orbitals combine to form bonding and anti-bonding molecular orbitals. The bonding orbital has lower energy and can accommodate both electrons with opposite spins, creating a stable H's molecule. The exclusion principle ensures that both electrons cannot have identical quantum states even though they occupy the same spatial orbital. Recent quantum chemical calculations using density functional theory have revealed the precise role of exclusion principle physics in chemical bond formation. Dr. Walter Kahn's computational methods show that approximately 20 to 40% of typical chemical bond energies arise from exchange effects directly related to exclusion principle constraints on electron behavior. But chemical bonding involves more than just electron sharing. It requires understanding how exclusion principle constraints determine molecular geometry and chemical reactivity. Dr. Ronald Gillespie's VSEP, or valence shell electron pair repulsion theory, explains molecular shapes through electron pair arrangements that minimize repulsion while satisfying exclusion requirements. The exclusion principle also explains why certain combinations of atoms can form stable molecules while others cannot. Consider the hypothetical He molecule. Although 2 helium atoms could theoretically share electrons in molecular orbitals, the exclusion principle requires that anti-bonding orbitals be occupied equally with bonding orbitals, resulting in no net bonding and explaining helium's chemical inertness. Dr. Robert Mulliken's molecular orbital theory provides the mathematical framework for understanding exclusion principle effects in chemical bonding. Molecular orbitals are constructed as linear combinations of atomic orbitals, and electron occupancy must satisfy exclusion constraints throughout the entire molecular system, not just within individual atoms. Recent advances in quantum chemistry have enabled direct calculation of how exclusion principle physics affects chemical reaction mechanisms. Dr. Roald Hoffmann's analysis of orbital symmetry shows that exclusion constraints determine which chemical reactions can proceed through allowed pathways and which are forbidden due to orbital overlap requirements. The exclusion principle also determines the phenomenon of electron pairing in chemical bonds. Dr. Linus Pauling's concept of covalent bonding relies fundamentally on electron pairs with opposite spins occupying bonding molecular orbitals. This pairing isn't accidental. It represents the maximum occupancy allowed by exclusion principle constraints for any quantum state. Understanding chemical bonding also reveals how exclusion principle effects create different types of bonds with characteristic properties. Ionic bonding occurs when exclusion pressure in electron shells makes electron transfer energetically favorable. Covalent bonding occurs when electron sharing in molecular orbitals lowers system energy while satisfying exclusion constraints. Metallic bonding emerges when exclusion principle physics creates delocalized electron bands in crystalline solids. Dr. Neville Mott's analysis of metal insulator transitions shows how exclusion principle constraints on electron behavior determine whether materials exhibit metallic conductivity or insulating behavior. The competition between kinetic energy favoring delocalization and Coulomb repulsion favoring localization occurs within exclusion principle constraints that fundamentally shape electronic behavior. Recent spectroscopic experiments using femtosecond laser pulses have enabled direct observation of chemical bond formation and breaking processes. Dr. Ahmed Seawale's Nobel Prize-winning work reveals how exclusion principle constraints influence the dynamics of chemical reactions by determining how electrons reorganize during molecular rearrangements. But chemical bonding also demonstrates how exclusion principle physics enables complex molecular architectures. Large molecules like proteins and DNA rely on networks of chemical bonds that satisfy exclusion requirements locally while creating global structures with emergent properties that exceed the sum of individual bonding interactions. Dr. Max Brutz's analysis of protein structure reveals how exclusion principle constraints on chemical bonding enable the complex three-dimensional architectures that support biological function. The specific geometries allowed by exclusion constraints determine how amino acids can connect to form stable protein folds with precise active site structures. The technological applications of exclusion principle chemistry appear throughout materials engineering and pharmaceutical design. Understanding how exclusion constraints determine molecular stability and reactivity enables rational design of new materials with desired mechanical, electrical, and chemical properties. Recent developments in computational drug design rely heavily on quantum chemical calculations that incorporate exclusion principle effects. Dr. Peter Kalman's molecular dynamics simulations show how exclusion constraints determine protein drug binding affinities through detailed modeling of electronic interactions in complex molecular systems, but chemical bonding also reveals fundamental connections between quantum mechanics and thermodynamics. The exclusion principle determines not only bond energies but also entropy contributions through constraints on how electrons can arrange themselves in molecular systems. This creates quantum statistical effects that influence chemical equilibria and reaction rates. Dr. Henry Eyring's transition state theory incorporates exclusion principle physics through quantum statistical mechanics of molecular vibrations and electronic states. The rates of chemical reactions depend on how exclusion constraints affect the energies and entropies of reactant, product, and transition state configurations. Understanding chemical bonding also illuminates how exclusion principle physics enables catalysis processes that accelerate chemical reactions without being consumed. Catalytic activity often depends on how exclusion constraints and catalyst electronic structure create favorable pathways for reactant transformation. Recent advances in single-molecule chemistry have enabled direct observation of individual chemical bonds forming and breaking under controlled conditions. Dr. Gerhard Erdel's surface science experiments reveal how exclusion principle constraints determine the elementary steps of catalytic processes at solid surfaces. The role of exclusion principle physics in chemical bonding extends beyond just ground-state molecular structures to include excited electronic states that determine photochemical processes. When molecules absorb light, electrons are promoted to higher energy orbitals while still satisfying exclusion constraints, creating excited states with different bonding characteristics. Dr. George Porter's flash photolysis experiments demonstrate how exclusion principle constraints determine the lifetimes and reactivity of electronically excited molecules. Photochemical processes must satisfy exclusion requirements for electron arrangements in both ground and excited states, creating selection rules that determine which photochemical reactions are possible. Modern quantum chemical methods now enable routine calculation of molecular properties that depend on exclusion principle physics. Dr. John Popole's computational methods for molecular orbital calculations incorporate exclusion constraints through self-consistent field approaches that determine optimal electron arrangements for complex molecular systems. But perhaps the most remarkable aspect of chemical bonding involves how exclusion principle constraints enable the emergence of complex chemistry from simple quantum mechanical rules. The vast diversity of molecular structures, chemical reactions, and materials properties all rise from exclusion principle requirements operating on electron arrangements in multi-atom systems. Recent discoveries in chemical topology reveal how exclusion principle constraints can create impossible molecular architectures, including catenanes, protohexanes, and knot-shaped molecules. These exotic structures exist because exclusion requirements permit electron arrangements that support topologically complex molecular geometries. Understanding chemical bonding also provides insights into how exclusion principle physics might operate in extreme environments, including high pressures, intense electromagnetic fields, and relativistic conditions. These extreme conditions test the universality of exclusion principle constraints in chemical bonding under conditions far from normal laboratory environments. As we prepare to explore how exclusion principle physics determines the mechanical properties of solid materials through crystalline bonding networks, remember that chemical bonding represents the direct translation of quantum mechanical principles into the molecular architectures that define the material world around us. The question that emerges from understanding chemical bonding is profound. If the exclusion principle determines not only which molecules can exist but also their shapes, reactivity, and properties, what does this reveal about the quantum mechanical foundations of all chemical and biological complexity? Solid state. The transition from individual molecules to solid materials represents a dramatic scaling up of exclusion principle physics, where quantum mechanical constraints operating on individual electrons create bulk properties like hardness, conductivity, and optical transparency that define our entire technological civilization through the collective behavior of trillions upon trillions of quantum particles obeying Pauli exclusion requirements. When atoms condense into crystalline solids, their electron shells didn't simply overlap, they merge into extended electronic structures that span the entire crystal while maintaining exclusion principle constraints throughout the solid. This creates energy bands where electrons can occupy continuous ranges of energy states, but each individual state can still accommodate at most 2 electrons with opposite spins. Dr. Felix Bloch's fundamental analysis in the 1930s showed that electrons in crystalline solids exist as delocalized waves extending throughout the crystal lattice. These Bloch waves represent quantum states that satisfy both the periodic boundary conditions imposed by crystal structure and the exclusion principle requirements that prevent multiple electrons from occupying identical quantum states. The mathematical framework describing solid-state physics involves solving Schrödinger equations for electrons moving in periodic potentials created by regularly arranged atomic cores. The solutions form energy bands separated by forbidden energy gaps, with each band capable of accommodating exactly 2 electrons per primitive unit cell, a direct manifestation of Pauli exclusion constraints. Recent angle-resolved photo-emission spectroscopy experiments have enabled direct measurement of electronic band structure in crystalline materials. Dr. Andreas Damascelli's measurements reveal the detailed energy-momentum relationships for electrons in solids, confirming theoretical predictions about how exclusion principle constraints create the band structures that determine materials' properties. But solid-state physics reveals how exclusion principle effects create dramatically different classes of materials depending on how electrons fill available energy bands. Metals occur when conduction bands are partially filled, allowing electrons to respond to external fields and carry electrical current. Insulators occur when valence bands are completely filled and conduction bands are completely empty, with energy gaps too large for thermal excitation. Dr. Neville Mott's Nobel Prize-winning work revealed that the transition between metallic and insulating behavior represents a fundamental quantum phase transition, driven by the competition between kinetic energy and Coulomb repulsion within exclusion principle constraints. The Mott transition demonstrates how exclusion physics can create qualitatively different electronic behaviors in the same material under different conditions. The exclusion principle also explains why solid materials exhibit mechanical strength and structural stability. When you apply force to a solid, you're attempting to compress electron clouds that are already constrained by exclusion requirements. The resulting Pauli repulsion creates mechanical resistance that prevents atoms from being pushed arbitrarily close together. Consider what happens when you try to compress a piece of metal. The exclusion principle forces electrons into higher energy states as available quantum states at lower energies become fully occupied. This creates degeneracy pressure that increases rapidly with compression, providing mechanical support that can withstand enormous applied forces. Dr. John Bardine's analysis of mechanical properties reveals that exclusion principle physics contributes significantly to bulk modulus, shear strength, and elastic constants of solid materials. The resistance to compression and deformation arises partly from electromagnetic forces between atoms, but also from purely quantum mechanical exclusion effects that prevent electron wave functions from overlapping beyond certain limits. Recent diamond anvil cell experiments have enabled studies of materials under pressures exceeding 1 million atmospheres. Dr. Russell Hemley's measurements reveal how exclusion principle constraints determine material behavior under extreme compression, including pressure-induced phase transitions and electronic property changes, but solid-state physics also demonstrates how exclusion principle requirements can create exotic quantum phases of matter with properties that have no classical analogs. Superconductivity emerges when electrons form Cooper pairs that circumvent normal exclusion constraints, enabling electrical conduction without resistance through collective quantum behavior. Dr. Leon Cooper's analysis showed that electron pairing in superconductors doesn't violate the exclusion principle but rather exploits a loophole, while individual electrons are fermions that obey exclusion. Electron pairs can behave as composite bosons that don't experience exclusion constraints. This enables macroscopic quantum coherence phenomena including zero electrical resistance and magnetic field expulsion. The technological applications of exclusion principle physics in solids extend throughout modern electronics and quantum devices. Semiconductor devices rely fundamentally on controlling electron occupancy of energy bands through doping, electric fields, and band structure engineering that exploits exclusion principle constraints on electronic behavior. Dr. Walter Brataine's transistor invention depends critically on exclusion principle physics that determines how electrons and holes behave at semiconductor interfaces. The amplification and switching properties that enable all digital electronics arise from exclusion constraints that determine carrier concentrations and transport properties in semiconductor devices. Recent advances in quantum materials research have revealed new phases of matter where exclusion principle physics creates topological electronic properties that are protected against disorder and imperfections. These topological materials could enable fault-tolerant quantum computing and dissipationless electronic devices. Dr. Duncan Haldan's analysis of topological band structures shows how exclusion principle constraints can create surface states with exotic properties including spin momentum locking and protection against backscattering. These effects emerge purely from exclusion physics operating in materials with specific crystalline symmetries. But solid-state physics also reveals how exclusion principle effects scale from atomic to macroscopic dimensions through collective electronic behavior. The properties we experience, whether a material is hard or soft, conducting or insulating, transparent or opaque, all emerge from exclusion principle constraints operating on electronic structure through extended crystalline networks. Understanding optical properties provides particularly clear examples of exclusion principle physics in solids. When light interacts with crystalline materials, photon absorption and emission processes must satisfy exclusion constraints on initial and final electronic states. This determines absorption spectra, optical conductivity, and transparency properties. Dr. Jen Tauka's analysis of optical absorption in semiconductors reveals how exclusion principle constraints determine band-edge properties that control transparency and absorption. The precise energies and intensities of optical transitions depend on exclusion determined occupancy of initial and final electronic states. Recent developments in metamaterials engineering exploit exclusion principle physics to create materials with electromagnetic properties that do occur naturally. By controlling electronic band structure through nanostructuring, researchers can engineer effective optical constants including negative refractive indices and cloaking behavior. Dr. John Pendry's analysis of metamaterials shows how exclusion principle constraints on electron behavior in artificial structures can create electromagnetic responses that transcend limitations of natural materials. These effects arise from collective electronic behavior in engineered nanostructures that amplify exclusion principle physics. The thermal properties of solids also reflect exclusion principle physics through electronic contributions to heat capacity and thermal conductivity. At low temperatures, the exclusion principle creates characteristic temperature dependencies in electronic properties that differ qualitatively from classical predictions. Dr. Arnold Sommerfeld's analysis of electronic heat capacity in metals revealed that exclusion principle constraints dramatically reduce electronic contributions to thermal properties. Compared to classical predictions, only electrons within approximately k_bt of the Fermi energy can contribute to thermal excitations, creating linear temperature dependence rather than classical 3/2 k_bt behavior. Understanding exclusion principle physics in solids also illuminates connections between electronic structure and magnetic properties. The magnetic moments of atoms in crystalline environments depend on how exclusion constraints determine electron spin arrangements in partially filled energy bands. Recent discoveries of exotic magnetic phases, including quantum spin liquids, reveal how exclusion principle physics can create magnetic states with no classical analogs. These phases emerge when exclusion constraints prevent conventional magnetic ordering while maintaining quantum mechanical correlations between electron spins. Modern computational materials science relies heavily on density functional theory calculations that incorporate exclusion principle physics through exchange correlation effects. Dr. Walter Kahn's methods enable prediction of materials properties by solving quantum mechanical equations that respect exclusion constraints for electronic structure in crystalline solids. But perhaps the most remarkable aspect of solid-state physics involves how exclusion principle constraints enable technological control over quantum mechanical properties at macroscopic scales. Modern devices can manipulate exclusion principle physics to create materials with engineered properties that enable quantum computing, energy harvesting, and information processing technologies. As we prepare to explore how exclusion principle physics creates the pressure that supports massive astronomical objects against gravitational collapse, remember that solid-state physics represents the scaling of quantum mechanical principles to macroscopic dimensions where exclusion constraints determine the mechanical, electrical, and optical properties of the material world. The question that emerges from understanding solid-state physics is profound. If exclusion principle constraints can determine all the bulk properties of materials that define our technological civilization, what does this reveal about the quantum mechanical foundations of macroscopic reality? Degeneracy pressure. The concept of degeneracy pressure represents one of the most extraordinary manifestations of the Pauli exclusion principle, a purely quantum mechanical force that emerges not from electromagnetic interactions but from the statistical requirements of fermion behavior, creating pressures so enormous they can support stellar masses against gravitational collapse and determine the ultimate fate of matter in the universe. Degeneracy pressure rises when fermions are compressed to densities where exclusion principle constraints force them into high-energy quantum states. And like classical pressure, which results from particle collisions and thermal motion, degeneracy pressure exists even at absolute zero temperature and emerges purely from the requirement that no two fermions can occupy identical quantum states. Dr. Ralph Fowler first recognized the importance of degeneracy pressure in 1926 when analyzing the puzzle of white dwarf stars, objects with masses comparable to our Sun compressed into volumes the size of Earth. Classical physics predicted that such objects should be gravitationally unstable, yet observations revealed them to be stable stellar remnants persisting for billions of years. The mathematical description of degeneracy pressure involves Fermi-Dirac statistics applied to ultra-dense matter. When fermion density increases, available quantum states at low energies become completely filled, forcing additional fermions into progressively higher energy states. The average energy per particle increases with density according to E varies as n to thirds, where n is the particle density. Recent calculations by Dr. Subramanian Chandrasekhar revealed that electron degeneracy pressure follows P equals S squared 5 meters underscore 3 to thirds N underscore 5 thirds, where N underscore is electron density. This pressure increases much more rapidly with density than classical thermal pressure, enabling degeneracy effects to dominate at sufficiently high compressions. But degeneracy pressure creates effects that seem to violate intuitive expectations about matter behavior. As you compress a degenerate fermion gas, its pressure increases even though temperature might remain constant or even decrease. This quantum pressure has no classical analog and emerges purely from exclusion principle constraints on particle arrangements. Degeneracy pressure. Dr. Enrico Fermi's analysis of nuclear matter revealed that neutron degeneracy pressure operates similarly to electron degeneracy pressure but at much higher densities, corresponding to nuclear density scales. The equation of state for neutron star matter depends critically on neutron degeneracy pressure competing against gravitational compression. Understanding degeneracy pressure requires appreciating that it represents a fundamental limit on matter compression imposed by quantum mechanics. No known force can compress fermions beyond the densities where exclusion principle constraints create degeneracy pressures comparable to the compressing forces. Recent observations of white dwarf stars have provided precise tests of degeneracy pressure physics. The Hubble Space Telescope measurements of white dwarf masses and radii confirmed theoretical predictions based on electron degeneracy pressure with remarkable accuracy, validating quantum mechanical calculations applied to stellar mass objects. The temperature independence of degeneracy pressure creates astronomical objects with properties unlike any terrestrial matter. White dwarf stars maintain surface temperatures of thousands of degrees while their interiors are supported by degeneracy pressure that doesn't depend on thermal energy. These objects represent quantum matter where statistical mechanics rather than thermodynamics determines bulk properties. Dr. Lev Landau's analysis of stellar structure revealed that degeneracy pressure creates fundamental limits on stellar evolution. The Chandrasekhar mass limit, approximately 1 point for solar masses for white dwarf stars, represents the maximum mass that electron degeneracy pressure can support against gravitational collapse. When stellar masses exceed the Chandrasekhar limit, electron degeneracy pressure becomes insufficient to prevent gravitational collapse. This forces protons and electrons to combine into neutrons through inverse beta decay, creating neutron stars where neutron degeneracy pressure provides support against further gravitational compression. Recent observations from the Laser Interferometer Gravitational Wave Observatory LIGO have detected neutron star mergers that provide direct tests of neutron degeneracy pressure under extreme conditions. Dr. David Shoemaker's analysis reveals gravitational wave signatures consistent with neutron star matter equations of state based on fermion degeneracy physics. But degeneracy pressure also operates in less exotic environments, including the interiors of planets and laboratory conditions achievable with intense laser compression. Understanding degeneracy effects has become crucial for inertial confinement fusion research where matter is compressed to densities approaching those found in stellar interiors. Dr. John Lindel's analysis of laser fusion experiments reveals that degeneracy pressure effects become important when deuterium-tritium fuel is compressed to densities exceeding 100 times that of solid density. At these compressions, exclusion principle constraints on nucleon behavior begin affecting the equation of state and fusion reaction rates. The quantum mechanical origin of degeneracy pressure can be understood through Heisenberg's uncertainty principle. When fermions are confined to smaller volumes, their position uncertainty decreases, which requires their momentum uncertainty to increase. This increased momentum corresponds to higher kinetic energy, creating pressure that resists further compression. Recent laboratory experiments using diamond anvil cells have achieved pressures comparable to those found in planetary interiors, enabling direct studies of degeneracy pressure effects in solid materials. Dr. Russell Hemley's measurements reveal how exclusion principle constraints modify the mechanical properties of materials under extreme compression, but degeneracy pressure also reveals fundamental connections between quantum mechanics and general relativity in extreme gravitational environments. When degeneracy pressure approaches relativistic limits, general relativistic effects become important, leading to modified pressure relationships and stability criteria. Dr. Chandrasekhar's relativistic analysis showed that electron degeneracy pressure becomes less effective at supporting stellar masses when electron velocities approach the speed of light. This creates an absolute upper limit on white dwarf masses beyond which no equilibrium configuration exists, forcing gravitational collapse to neutron star or black hole states. The experimental study of degeneracy pressure in laboratory conditions has become possible through advances in high-pressure physics and laser-driven compression techniques. These experiments reveal how exclusion principle physics scales from atomic to macroscopic dimensions under extreme conditions. Recent experiments by Dr. Raymond Jeanlos using laser-driven shock waves have achieved pressures exceeding 10 million atmospheres in laboratory samples, enabling direct studies of how degeneracy pressure affects material properties under conditions approaching those found in planetary interiors and stellar remnants. Understanding degeneracy pressure also illuminates fundamental questions about the limits of matter stability and the ultimate fate of compressed matter in the universe. If neutron degeneracy pressure can be overcome by sufficiently strong gravitational fields, what exotic forms of matter might exist in the cores of the most massive compact objects? Theoretical investigations of exotic matter phases including quark matter and strange matter suggest that new forms of degeneracy pressure might operate at densities exceeding nuclear density. Dr. Frank Wilczek's analysis of quantum chromodynamics predicts that quark degeneracy pressure could support matter configurations with properties even more extreme than neutron stars. Recent astrophysical observations have revealed compact objects with masses and radii that challenge conventional neutron star models, suggesting possible exotic matter phases where different forms of degeneracy pressure might operate. These observations provide natural laboratories for testing quantum mechanics under the most extreme conditions imaginable. But degeneracy pressure also demonstrates how quantum mechanical principles can determine macroscopic phenomena across enormous scales of space and time. The exclusion principle operating on individual fermions determines the structure and evolution of stellar objects with masses exceeding 1,030 kilograms and lifetimes exceeding billions of years. Modern computational astrophysics relies heavily on accurate equations of state that incorporate degeneracy pressure effects. Dr. James Latimer's calculations of neutron star structure require precise modeling of how exclusion principle constraints determine matter properties at densities up to 10 times nuclear density. Understanding degeneracy pressure also provides insights into exotic quantum phases that might exist under extreme conditions. Theoretical predictions suggest that sufficiently compressed matter might undergo phase transitions to quantum states with properties that have no terrestrial analogs. Recent developments in ultra-cold atomic physics have enabled laboratory studies of degenerate fermion gases where degeneracy pressure effects can be directly observed and controlled. Dr. Deborah Ginnes' experiments with ultra-cold atoms provide quantum gas microscopes that reveal how exclusion principle constraints determine pressure relationships in controlled quantum systems. But perhaps the most profound aspect of degeneracy pressure involves what it reveals about the relationship between quantum mechanics and cosmic evolution. The existence of stable white dwarf and neutron stars depends entirely on quantum mechanical effects operating on astronomical scales, demonstrating deep connections between microscopic physics and cosmic structure formation. As we prepare to explore how the same exclusion principle physics that creates degeneracy pressure in stars also operates in solid materials to create the mechanical properties we experience in everyday objects, remember that degeneracy pressure represents one of the most direct manifestations of quantum mechanical principles operating at cosmic scales. The question that emerges from understanding degeneracy pressure is profound. If purely quantum mechanical effects can support stellar masses against gravitational collapse, what does this reveal about the fundamental role of quantum mechanics in determining the large-scale structure and evolution of the universe? Material properties, the mechanical, thermal, electrical, and optical properties of all materials are on us, from the hardness of diamond and the flexibility of rubber to the transparency of glass and the conductivity of copper emerge directly from how the Pauli exclusion principle constrains electron arrangements in crystalline structures, creating the rich diversity of material behaviors that define our technological civilization and enable complex chemistry and biology. The hardness of materials provides one of the most direct examples of exclusion principle physics in everyday experience. When you press on a solid surface, you're attempting to compress atomic electron clouds that are already constrained by Pauli exclusion requirements. The resistance you feel emerges largely from quantum mechanical forces that prevent electrons from occupying identical states as atomic separation decreases. Dr. Max Born's analysis of crystal lattice vibrations revealed that mechanical properties like elastic modulus and bulk compressibility depend fundamentally on how exclusion principle constraints determine electron distribution around atomic nuclei. The spring constants characterizing interatomic forces in solids include significant contributions from exclusion-related effects that have no classical analogs. Diamond represents perhaps the most dramatic example of exclusion principle physics determining material properties. The extraordinary hardness of diamond emerges from carbon atoms arranged in a three-dimensional network where each carbon forms four covalent bonds in tetrahedral geometry. Each bond involves electron pairs constrained by exclusion requirements, creating mechanical resistance that can withstand enormous applied forces. Recent nano-indentation experiments by Dr. William Oliver have enabled precise measurements of how exclusion principle physics contributes to materials' hardness by applying forces with nanometer-scale spatial resolution. These experiments reveal that mechanical resistance emerges partly from electromagnetic repulsion, but significantly from quantum mechanical exclusion effects. But material properties extend far beyond just mechanical behavior to include electrical conductivity, which depends entirely on how exclusion principle constraints determine electron mobility in crystalline structures. Metals conduct electricity because their electrons occupy partially filled energy bands where exclusion principle allows electron motion in response to applied electric fields. The difference between metals, semiconductors, and insulators emerges entirely from how exclusion principle requirements determine electronic band structure. Dr. Alan Wilson's analysis showed that electrical conductivity depends on whether valence electron bands are partially filled metals, completely filled with small energy gaps to empty bands semiconductors, or completely filled with large energy gaps insulators. Recent transport measurements using quantum point contacts have enabled studies of electrical conduction at the single electron level. Dr. Bart van Wees's experiments reveal how exclusion principle constraints determine conductance quantization in nanoscale structures, providing direct observation of quantum mechanical effects in electronic transport. Thermal properties of materials also reflect exclusion principle physics through electronic contributions to heat capacity and thermal conductivity. The Sommerfeld model of metals shows that exclusion principle constraints dramatically reduce electronic heat capacity compared to classical predictions because only electrons near the Fermi energy can participate in thermal excitations. Dr. Charles Kittle's analysis of solid-state physics demonstrates that exclusion principle effects determine temperature dependencies of numerous materials' properties. Electronic heat capacity varies linearly with temperature rather than classically. Phone and heat capacity follows Debye models that incorporate exclusion constraints on lattice vibrational modes, and thermal expansion reflects how exclusion physics responds to thermal energy. The optical properties of materials provide particularly clear demonstrations of exclusion principle physics determining macroscopic behavior. Transparency, absorption, and reflection depend on how exclusion constraints determine electronic transitions between occupied and unoccupied quantum states. Consider why glass is transparent while metals are opaque. Glass has completely filled valence bands and empty conduction bands separated by energy gaps larger than visible light photon energies. Exclusion principle constraints prevent optical transitions because no empty states exist at energies corresponding to visible light. Metals have partially filled bands where exclusion requirements allow optical transitions at all visible frequencies. Recent ultra-fast spectroscopy experiments by Dr. Ahmed Ziwel have enabled direct observation of how exclusion principle constraints determine optical response on femtosecond timescales. These experiments reveal how electron arrangements constrained by Pauli exclusion determine the dynamics of optical absorption and emission processes. But material properties also demonstrate how exclusion principle physics can create behaviors that seem impossible according to classical expectations. Superconductivity emerges when electron pairing enables circumvention of normal exclusion constraints, creating electrical conduction without resistance and magnetic field expulsion phenomena. Dr. John Bardine's BCS theory of superconductivity shows that Cooper pair formation doesn't violate exclusion principle but rather creates composite bosonic objects that don't experience fermionic exclusion constraints. This enables macroscopic quantum coherence phenomena including zero electrical resistance and flux quantization. The technological applications of exclusion principle physics in materials extend throughout modern electronics, energy technologies, and manufacturing processes. Semiconductor devices rely fundamentally on controlling electron occupancy of energy bands through exclusion principle constraints modified by doping, electric fields, and quantum confinement effects. Recent advances in quantum materials engineering have enabled creation of artificial materials with properties determined by designer exclusion principle physics. Quantum wells, quantum dots, and quantum wires confine electrons in structures where exclusion constraints can be controlled through device geometry and external fields. Dr. Leo Kouwenhoven's experiments with quantum dots demonstrate that exclusion principle physics applies to artificial atomic structures created through semiconductor nanoengineering. These artificial atoms exhibit shell structure, magic number effects, and chemical bonding analogous to natural atoms but with controllable parameters. Understanding material properties also reveals how exclusion principle physics enables complex chemical and biological systems. The mechanical properties of biological materials from bone and cartilage to proteins and cell membranes depend on exclusion principle constraints that determine how molecules can pack together and respond to applied forces. Dr. Stephen Vogel's analysis of biomechanics shows that biological materials exploit exclusion principle physics to achieve remarkable combinations of strength, flexibility, and toughness. Collagen fibers, chitin structures, and protein networks all depend on exclusion constraints that determine molecular arrangements and mechanical responses. Recent advances in materials science have revealed how exclusion principle physics can create smart materials that respond to environmental changes through controlled modifications of electronic structure, shape memory alloys, photochromic materials, and piezoelectric ceramics all exploit exclusion principle constraints that couple electronic, structural, and mechanical properties. The magnetic properties of materials provide additional examples of exclusion principle physics determining macroscopic behavior, ferromagnetism, antiferromagnetism, and paramagnetism emerge from how exclusion constraints determine electron spin arrangements in crystalline structures with partially filled electronic bands. Dr. Louis Neal's analysis of magnetic materials shows that exclusion principle requirements determine magnetic ordering patterns through exchange interactions that depend on electron wave function. Overlap constrained by Pauli exclusion, the temperature dependencies of magnetic transitions reflect how thermal energy competes with exclusion-determined exchange energies. But material properties also demonstrate fundamental connections between quantum mechanics and thermodynamics through exclusion principle effects on phase transitions and critical phenomena. Many materials undergo structural or electronic phase transitions driven by competition between exclusion-related energies and thermal effects. Recent high-pressure experiments have revealed how exclusion principle constraints determine materials' behavior under extreme conditions. Diamond anvil cell studies by Dr. Russell Hemley show that exclusion physics can drive pressure-induced phase transitions that create materials with properties dramatically different from ambient conditions. Understanding exclusion principle physics in materials also illuminates how quantum effects can be amplified from atomic to macroscopic scales through collective behavior in crystalline structures. Individual exclusion constraints operating on single electrons create bulk properties that determine the mechanical, electrical, and thermal behavior of macroscopic objects. Modern computational materials science relies heavily on density functional theory calculations that incorporate exclusion principle physics through exchange correlation functionals. Dr. Walter Kohn's methods enable prediction of materials' properties by solving quantum mechanical equations that respect exclusion constraints throughout crystalline structures. Recent discoveries of topological materials reveal how exclusion principle physics can create electronic properties that are protected against disorder and defects. These materials exhibit surface states with exotic properties that could enable fault-tolerant quantum devices and dissipationless electronic transport. But perhaps the most remarkable aspect of material properties involves how exclusion principle constraints enable the rich diversity of behaviors that make complex technology and biology possible. The fact that carbon can form both soft graphite and hard diamond, that silicon can be either insulating or conducting depending on doping, and that the same atoms can create materials with vastly different properties all reflects exclusion principle physics operating in different structural contexts. As we prepare to explore how exclusion principle physics operates in quantum devices and enables quantum computing technologies, remember that the material properties we've examined represent the direct translation of quantum mechanical principles into the macroscopic behaviors that define our technological civilization. The question that emerges from understanding material properties is profound. If all the mechanical, electrical, thermal, and optical properties of materials emerge from exclusion principle constraints on electron arrangements, what new technologies might become possible as we develop better methods for controlling quantum mechanical structure in artificial materials? The development of quantum devices represents the most sophisticated technological exploitation of Pauli exclusion principle physics, where engineers deliberately manipulate exclusion constraints on electron behavior to create devices that operate through pure quantum mechanical effects, enabling technologies from quantum computers and ultra-sensitive magnetometers to single photon detectors and quantum communication systems. Quantum devices work by controlling exclusion principle physics at the level of individual electrons and photons, creating systems where quantum mechanical effects that are normally averaged out in bulk materials become the primary mechanism for device operation. This requires engineering structures at atomic scales where exclusion constraints can be precisely controlled and manipulated. The foundation for quantum device engineering was established by Dr. Leo Isaki's discovery of quantum tunneling in semiconductor junctions, when electrons encounter potential barriers in crystalline structures. Exclusion principle constraints determine their quantum mechanical behavior, enabling tunneling phenomena that create negative resistance effects impossible in classical electronics. Recent advances in quantum dot fabrication have enabled creation of artificial atoms where exclusion principle physics can be controlled through external electric and magnetic fields. Dr. Mark Kastner's experiments demonstrate that quantum dots exhibit atomic-like properties, including discrete energy levels, shell structure, and magic number effects that emerge from exclusion constraints on confined electrons. But quantum devices also exploit collective exclusion principle effects to create macroscopic quantum phenomena. Superconducting quantum interference devices (SQUIDs) operate through Cooper pair formation that enables electrons to circumvent normal exclusion constraints, creating systems where macroscopic quantum coherence can be maintained and controlled. Dr. John Clark's analysis of SQUID magnetometers reveals how exclusion principle physics enables magnetic field measurements with sensitivities approaching fundamental quantum limits. These devices can detect magnetic fields smaller than those produced by single electron spins, demonstrating how exclusion constraints can be exploited for ultra-sensitive quantum sensing. Quantum computing represents perhaps the most ambitious application of exclusion principle physics in technological systems. Quantum qubits often rely on electron or nuclear spin states that obey exclusion constraints, enabling quantum superposition and entanglement phenomena that provide exponential computational advantages for certain algorithms. Recent developments in silicon quantum dots have enabled creation of electron spin qubits where exclusion principle physics determines quantum coherence properties. Dr. Andrew Durak's experiments show that single electrons confined in silicon quantum dots can maintain quantum superposition states for milliseconds while remaining controllable through electrical signals. But quantum devices also demonstrate how exclusion principle constraints can create exotic collective phenomena with no classical analogs. The fractional quantum Hall effect emerges when electrons in two-dimensional systems form correlated liquid states that exhibit fractional charge excitations through exclusion principle physics operating in strong magnetic fields. Dr. Horst Sturmer's Nobel Prize-winning experiments revealed that fractional quantum Hall states create anyons, exotic quasiparticles that obey statistical behavior intermediate between fermionic and bosonic. These states emerge purely from exclusion principle constraints operating on electrons in two-dimensional semiconductor structures under intense magnetic fields. Understanding quantum devices also reveals how exclusion principle physics can enable quantum error correction and fault-tolerant quantum computing. Topological quantum computing proposals exploit exclusion constraints to create quantum states that are naturally protected against certain types of decoherence and errors. Dr. Alexei Kitaev's theoretical analysis shows that topological quantum devices could use exclusion principle physics to create topologically protected qubits, where quantum information is stored in global properties of many electron wave functions rather than local properties of individual particles. Recent experiments in quantum communication exploit exclusion principle constraints on photon behavior to enable secure information transmission through quantum key distribution protocols. Single photon detectors rely on exclusion physics in semiconductor devices to achieve detection efficiencies approaching fundamental quantum limits. The technological challenges of quantum device engineering often involve maintaining quantum coherence while controlling exclusion principle effects at the level of individual particles. Dr. David Wineland's ion-trap quantum computers demonstrate how exclusion constraints can be controlled using electromagnetic fields to create scalable quantum computing architectures. But quantum devices also reveal fundamental connections between exclusion principle physics and quantum information theory. The no-cloning theorem that prevents perfect copying of a known quantum states emerges partly from exclusion constraints that determine how quantum information can be distributed among fermionic systems. Recent advances in quantum sensing have demonstrated how exclusion principle physics can enable measurements with precision beyond classical limits. Nitrogen vacancy centers in diamond exploit exclusion constraints on electron spins to create magnetometers and thermometers with single-atom sensitivity. Dr. Mikhail Lukin's experiments with nitrogen vacancy centers show how exclusion principle constraints on electronic structure enable quantum sensing of magnetic fields, electric fields, and temperature with spatial resolution approaching the atomic scale and temporal resolution in the microsecond range. Understanding quantum devices also illuminates how exclusion principle physics can enable quantum simulation of complex many-body systems that are impossible to calculate using classical computers. Ultra-cold atom systems provide controllable quantum platforms where exclusion constraints can be engineered to simulate condensed matter physics and quantum field theory. Dr. Emmanuel Bloch's quantum gas microscopy experiments demonstrate that ultra-cold fermions and optical lattices provide quantum simulators where exclusion principle physics can be directly observed and controlled at the single particle level, enabling studies of quantum phase transitions and exotic quantum phases. But quantum devices also demonstrate how exclusion principle constraints can be exploited for energy conversion and harvesting applications. Thermoelectric devices rely on exclusion principle physics that determines how electron transport properties depend on temperature gradients in semiconductor materials. Recent developments in quantum thermoelectrics have revealed how exclusion constraints in quantum dot systems can enhance energy conversion efficiency beyond classical limits. Dr. Kang Wang's experiments show that quantum confinement effects can optimize exclusion principle physics for improved thermoelectric performance. The role of exclusion principle physics in quantum devices extends beyond just electronic systems to include photonic and hybrid quantum devices. Single photon sources and detectors often rely on exclusion constraints in semiconductor quantum dots that determine optical transition properties and photon emission statistics. Dr. Peter Mitchell's experiments with quantum dot single photon sources demonstrate how exclusion principle constraints determine photon antibunching and indistinguishability properties that are crucial for quantum communication and quantum computing applications using photonic qubits. Recent advances in quantum device integration have enabled creation of quantum processors that exploit exclusion principle physics across multiple physical platforms simultaneously. Hybrid quantum systems combine trapped ions, superconducting circuits, and semiconductor quantum dots to create quantum devices with capabilities exceeding any single platform. Understanding quantum devices also reveals how exclusion principle physics might enable quantum technologies with revolutionary capabilities, including quantum internet, quantum radar, and quantum-enhanced sensing networks. These applications require maintaining quantum coherence across macroscopic distances while controlling exclusion constraints at the single particle level. Modern quantum device fabrication increasingly relies on atomic-scale engineering that directly manipulates exclusion principle physics through materials design and nanostructure fabrication. Dr. Charles Marcus's experiments with topological superconductor devices demonstrate how exclusion constraints can be engineered to create exotic quantum phases useful for quantum computing. But perhaps the most profound aspect of quantum devices involves how they demonstrate the technological potential of quantum mechanical principles that seemed purely academic when first discovered. The exclusion principle physics that Pauli formulated to understand atomic spectra now enables technologies that could revolutionize computing, communication, and sensing. Recent theoretical proposals for quantum device applications extend to exotic possibilities, including quantum batteries, quantum heat engines, and quantum-enhanced metrology that could enable measurements with precision limited only by fundamental quantum mechanical uncertainty principles rather than classical noise sources. Understanding quantum devices also illuminates fundamental questions about the boundary between quantum and classical physics in technological systems. These devices operate in regimes where exclusion principle constraints determine macroscopic behavior, revealing how quantum mechanics can be harnessed for practical applications despite decoherence and environmental effects. As we prepare to explore how exclusion principle physics operates in biological systems and enables complex biochemical processes, remember that quantum devices represent humanity's most sophisticated efforts to control and exploit quantum mechanical principles for technological applications. The question that emerges from understanding quantum devices is profound. If exclusion principle physics can be controlled to enable quantum computing, quantum sensing, and quantum communication technologies, what other revolutionary applications might become possible as we develop more sophisticated methods for manipulating quantum mechanical effects at macroscopic scales?